Class, I want to cover section 3.4 properties of rational functions. So a rational function is a function of this form where the P and the Q are both polynomial functions that we just covered, polynomial functions. And Q is not equal to the zero polynomial, so Q can't be zero because we can't divide by zero. The domain of a rational function is a set of all real numbers except those for which the denominator Q is zero. So we may have to exclude some values from the domain, and we will if they make the domain equal to zero. So this is actually the graph of like the most basic rational function, like for the most basic quadratic function, we had y equal x squared, y equal 1 over x is the most basic rational function. And rational functions have special things. They have asymptotes. So you notice how the graph is starting to flatten out as x goes to infinity. So this is x going to infinity this way. It's doing the same thing over here as x goes to negative infinity. So x is going to negative infinity this way. And the graph is flattening out. It almost looks linear. It isn't linear, but it's starting to look linear. And what we call this is a horizontal asymptote. And the equation of that horizontal asymptote is y equals 0. So horizontal asymptotes are going to be horizontal lines, and horizontal lines go y equal. Now, there's another asymptote for the rational functions, or there may be, and there is in this case. Right here, we have x equals 0. And notice that as x approaches 0, and we call this coming from the plus, meaning coming from numbers that are greater than 0, or you can think of it as coming from the right. What happens to the y is that the y is going to infinity. And now notice over here as x approaches 0 from the left, and what that means is numbers that are less than 0 or numbers to the left of 0, the y is going to negative infinity. So if we have this happening, and with the rational function, we will have this usually happening, not always, then if there's some value, and it would be the value that makes the denominator equal to 0, in this case, the value that makes the denominator equal to 0 is 0. So x cannot be 0. 0 is not in the domain of this function. But if, as x approaches 0, either the y values are getting bigger and bigger without bound, or they're getting, they're getting more and more negative without bound, then that is what we call a vertical asymptote. So we've got vertical asymptotes and we've got horizontal asymptotes. And a rational function may have both. It could have neither. So anyways, this is what we're talking about. Now, the domain of this function, tilt like this. The domain would be, if we look at it, it's everything except it skips over 0. Notice it gets closer and closer to 0. X gets closer and closer to 0, coming in from the right and coming in from the left, but it is never going to be 0. Because if it were 0, the function would be undefined. So the domain is from negative infinity to 0, and then we don't include 0, and then union with 0 to infinity. So that's the domain. Now, we need to look at the graph to see the range. So the range in this case is going to be everything except where that horizontal asymptote is, which is at y equals 0. So, because the function here, it can't actually, a function will, or a rational function will never cross its vertical asymptote. It can't, because it would be undefined at the vertical asymptote. it is possible for a function to graph, cross its horizontal asymptote. So it actually could come down and then come back up. But we're not really going to look at those that much, but it is possible. So the range, let's talk about the range, would be actually the same thing, from negative infinity to 0, union with 0 to infinity. That would be the range in this case. They're not always the same. But if you notice, for the domain, it's every value for the domain except for the vertical asymptote. And for the range, it's every value for the range except the horizontal asymptote. Okay, let's look at, this is from the table on the calculator for the graph of this function. Sorry, guys. Hold on just a minute. I lost it there for a second. Here we go. Okay, so let's get, try to get back. It's like if I move, it doesn't like it. Okay, let's look at this. This is from the graph of y equal 1 over x. And notice that as x gets bigger in the positive way, the y goes to 0, and we say from positive numbers greater than 0 is really what we're saying, numbers greater than 0. So look at this, the x is getting bigger going up this way. The x is getting bigger going this way. And the y value is getting closer and closer to 0. So we see that the y is going to 0. But it's coming in from positive numbers, numbers greater than 0. And this here is y going to negative infinity. And we see that as y is going to negative infinity, and I'll write that out as, or actually, I meant x going to negative infinity, not y. As x goes to negative infinity, the y is going to 0, but we say from the left. That means from the left. This means from the right. So it's coming in to 0, the y value. So see, these are getting smaller and smaller, but we're coming in from the numbers less than 0. So these numbers are, y is going to 0. Okay, and on a number line, when we're talking about this, for the y is going to 0 from the left, and then this way, y is going to 0 from the right. So it just means y is coming into 0 from the left, or y is coming into 0 from the right. If you just think about it, the numbers on a number line. Okay, let's go to the next page and read about some things. So this is 3.4. I know some of the writing here is not real great, or the print didn't come out very well. I don't know why. Maybe we need a new ink cartridge on our printer. I'm not sure, but we'll try to get by here. And you know, the written or the printed notes are in a PDF on iCollege. So we've already talked about end behavior with polynomials. So we can talk about end behavior with rational functions. And so note that as x gets more positive, the y values get smaller and approach 0. So as x is getting bigger, then the whole thing's going to be getting smaller. And if x is positive and getting bigger, the whole thing is getting smaller. You know, it's kind of like if you have one pizza and people keep coming into the room wanting a slice of pizza, then the slices are going to get smaller. And that's how I kind of think about that. As x gets more negative, the y values get larger and approach 0. So, I mean, that's kind of hard to relate with the pizza. But basically what we're saying is as the absolute value of x gets larger, then the y value is going to get smaller. So we state that as x goes to infinity, so the denominator is getting bigger, the y is going to go to 0. As x goes to negative infinity, that's a negative infinity right there, the y is going to go to 0. So this is what we mean by a horizontal asymptote. So a horizontal asymptote is really a type of end behavior if the graph has one. So it's a type of end behavior because it's what the graph is doing as we go off the graph. Like look at this picture over here. When we're talking about the horizontal asymptote, this is just what I just covered. We're talking about what's happening is either we're going off the edge, the end of this side, or the end on the other side. So it's the end behavior is what I'm trying to say. So if we look at this table and what's happening here, so this is still y equal 1 over x. And we've we've got as x goes to 0 from the left, the y is going to negative infinity. And we've already talked about this. As x goes to 0 from the right, y is going to positive infinity. And here we have it. The x is getting smaller and smaller, and the y is getting larger and larger. And if we have the x get smaller and smaller coming in from the negative direction, then the y is getting larger but negative. And then right here we have an error when x is actually 0. So looking right here, what's happening is x is going to 0. And what's coming in right here, x is going to 0. It's just from different. This one is coming in 0 from numbers less than 0. This is coming into 0 from numbers greater than 0. So we say, and now I lost you again. Oh, 1 minute. So as x gets closer to 0 from the right side, the y values get larger and tend to positive infinity. As x gets closer to 0 from the left side, the y values get more negative and tend to negative infinity. We state that as x goes to 0 from the right, y goes to infinity. As x goes to 0 from the left, there's a little minus sign right here, y goes to negative infinity. These plus and minus signs do not mean necessarily positive and negative, and we'll look at an explanation of that because x could be approaching numbers other than 0. But if this is true, then that means that the graph has a vertical asymptote. And now the vertical asymptote does not have to be 0, which we'll see in just a minute. And then the definition, let's just look at the definition here. And I've already read this. So let R denote a function as x goes to negative infinity or as x goes to infinity. And this is if that's true, the values of the function approach some fixed number L, then the line y equals is a horizontal asymptote. And if as x approaches some number c, the values, absolute value of R of x approaches infinity, which means that it's either approaching negative infinity or infinity, then the line x equals c is a vertical asymptote of the graph of R. Now, the graph of R never intersects a vertical asymptote, and we just talked about that. Okay, so let's go on to the next page. So how do we locate the vertical and the horizontal asymptotes? That's important, and we need to learn how to do that. So here's a typical rational function. Now, if it's in lowest terms, it will have a vertical asymptote x equal r if r is a real zero of the denominator q. So you have to factor the numerator and the denominator and cancel out any common factors to get it in lowest terms. And then if x minus r is a factor of the denominator, then you'll have a vertical asymptote at x equal r. Now, finding a horizontal, and we're not going to worry about the oblique asymptotes in this class. So finding the horizontal asymptotes, it's completely different from finding the vertical asymptotes. So really the vertical asymptotes, all we have to do is find where the denominator equals zero. If it's possible for it to be zero, we'll see some instances where the denominator would never be zero. But most of the examples we'll see where it could be zero, and at those values, we have the vertical asymptote. Now, and we don't talk about this in this class, but in calculus we do. Actually, when the denominator equals zero, if it's not in lowest terms, it could have a hole as well, but we're not going to talk about that. You know, we'll see some graphs that have holes, which means it's not defined at some value of x. We've already seen that. And if it's a rational function, that means that it's because the denominator is not defined there. But consider a rational function where we've got a polynomial in the numerator and a polynomial in the denominator. So all we really need to look at are these two first terms in the numerator and the denominator, and meeting the leading term. So it has to be in the right order. Now, so we're going to call the degree of the numerator n, and we're going to call the degree of the denominator m. Okay, so we compare the degree of the numerator with the degree of the denominator. And if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is the horizontal asymptote. Now, if the degrees are equal, then the line y equal the leading coefficient in the numerator divided by the leading coefficient in the denominator is a horizontal asymptote. So if they have the same degree, this is what's going to happen. That is, the horizontal asymptote equals the ratio of the leading coefficients. So just like, you know, when we were talking about end behavior, we were looking at the leading term. Well, remember, horizontal asymptote is a type of end behavior, and we're also looking at the leading term, or really you could think of this whole thing as a leading term. But what we're doing is we're comparing the numerator leading term with the denominator leading term. Now, then there's one other case. Well, let's don't worry about this because we're not going to worry about the oblique asymptotes. But if, so really what we're going to worry about right here is just if n is greater than m, then there will not be a horizontal asymptote. And the end behavior will resemble the power function a sub n over b sub m x to the n minus m. So remember how we determined the end behavior there, depending on whether this was even or odd and whether the leading coefficient was positive or negative. So remember, we had even, and then we had odd, and then underneath that, we had a sub n positive, or a sub n, or I guess in this case, it's going to be a sub n divided by b sub m. So a sub n over b sub m positive. Or the other case would be a sub n over b sub m negative. And then we'd have the same cases over here for odd. So remember that when we were talking about polynomials and end behavior. So a rational function will never have both a horizontal asymptote and an oblique asymptote. We're not going to worry about the oblique, so you can just forget about that if you want. Now, so here's a little example. So let's say that f of x equals 3x plus 5 over x minus 6. And you want to have the numerator in standard form and the denominator in standard form. Okay, the horizontal asymptote is going to be y equals 3 over 1, or which y equal 3, because this coefficient down here is 1, so y equal 3 over 1. That's the horizontal asymptote. Now the vertical asymptote, you just take the denominator. I mean, in real life, you need to factor and get it in the lowest form, but we're not really going to have to worry about that. So the vertical asymptote is going to be where the denominator is 0. So that's at x equals 6. And I should say that you may have more than one vertical asymptote for a rational function. So let's go to the next page. This is just a picture of vertical and horizontal asymptote. Yes, touch things. All right, we're going to okay, so this is the line x equals c. So this says x equals c. Is a vertical asymptote. Now, what it's just saying, and so this is that x is approaching c from less than c, or from the left. The y is going to infinity. Okay, that's one thing that could happen. But there's other things that could happen, like in this example right here. This is as x approaches c, also from the left, because we're to the left, or numbers less than, x values less than c. But in this case, the y is going to negative infinity. And still, x equals c is, I'm going to just abbreviate vertical asymptote. Now, it could be, like in this case, x is approaching c from the right, and the y is going to positive infinity. X equals c is a vertical asymptote. And then down here, what we've got is x is approaching c from numbers greater than c, but the y value is going to negative infinity. So here we still also have x equals c is a vertical asymptote. So just different pictures of how vertical asymptote can look. Now, like the one that we looked at just a minute ago, y equal 1 over x. Let's look at that picture again. This is y equal 1 over x. And we see that at the vertical asymptote, it's doing one thing on one side and another thing on the other side. That may be true. Or it may be doing the same thing on both sides. Or maybe it's not even defined over here. We'll see some functions like that when we get into logarithmic functions. So, and exponential functions. So let's look at the next thing. So that was about the vertical asymptotes. And then for the horizontal asymptotes, this is the way it might look. And let me just for you guys. Okay, so the line y equal, and gosh, I can't even read what it's supposed to say now. Y equal, I think that's supposed to be a D right there. So as x is going to negative infinity, the y is approaching D. That's what's happening right here. So it's either, we're either going to be going out to negative infinity or to positive infinity. And this is a horizontal, y equal D is a horizontal asymptote. Or it could be that we're coming in and becoming linear, but the graph is actually below the horizontal asymptote. So this is still a horizontal asymptote. But either way, the y is approaching D. So as x goes to infinity, or x goes to negative infinity. And so you notice I wrote it different up here. I wrote as x goes to negative infinity, y goes to D. Or y goes to D as x goes to negative infinity. You can say it either way. And then here we could also be going, it could be as x goes to positive infinity, that the y is approaching D. But either way, this y equal D, that's a horizontal asymptote. And then here, similar, but where the graph is actually below the horizontal asymptote. So we would say as x goes to infinity, y approaches D, just like we were talking about a minute ago. So talk a lot about the vertical and horizontal asymptotes. And then we've already been talking about this notation with the plus and minuses, but this is just a little chart explaining it again, what these symbols mean. So that's a plus sign. This is a minus. And this means as x approaches whatever C is from the right, but does not reach C. So like for instance, if this is 0, this would be x approaching 0 from the right. But if we're coming in this way, this would be x approaching 0 from the left. And it doesn't have to be 0. It could be some other number, like say 2. And then x would be approaching 2 from the right. Or if it's coming in this way, x is approaching 2 from the left. And then, of course, as x approaches infinity, it's just going this way, you know, and going out this way. This would be as x approaches negative infinity, just going out this way. Okay. And then let's look at another function that, or actually, first let's look at this. It is another function, but it's a transformation of y equal 1 over x. So just like when we were talking about transformation, in the rest of the class, we're talking about transforming some basic function, or you could call it a parent function or the original function. And so in this case, with the rational functions, so you know, like with the so you know how we were talking about like with the quadratic function, the basic function would be y equal x squared. Here, the original function is y equal 1 over x. And now we're also going to look at y equal 1 over x squared, but I know that this is a transformation of 1 over x because the x here in the denominator is not squared. So let's rewrite it in this order. Let's write it like this because I think it's better to see what the transformations are written this way. So if we talk about the transformations, so it shifted left 1 unit, And then we're starting with the inside. And notice here, the fraction bar is the grouping symbol. So if you're adding underneath the fraction bar to the x, adding or subtracting, it's going to shift left to right, just like when we were adding inside the grouping symbol for square root or absolute value or square function or whatever. And then the minus sign is just out in front of the function. It could be up there with the 1, but basically it's out here somewhere, You've got a negative in front of the 1 over x plus 1. So the way it works is first you're going to shift to the left 1 unit, then it's going to reflect across the x-axis. Because remember, if we are multiplying on the outside by -1, it reflects across the x-axis. And then this plus 2 is just going to shift up 2 units. Now, one thing about graphing rational functions and with the transformations is that you have to figure out what happens with the horizontal and the vertical asymptotes. And when you shift up or down, it affects the horizontal asymptotes. But when you shift left or right, it affects the vertical asymptotes. So the first thing we need to figure out is, well, let's just graph the transformations. Then we will see where the vertical asymptote is going to be. It's going to be at x equal -1. So why don't we go ahead and put that in? The vertical asymptote is x equal -1. Okay, we know that because if you set the denominator equal to 0, you get x equal -1. So one part in graphing this is to go ahead and draw in your vertical and horizontal asymptote. Now, because we shifted up 2 units, the normal, and we saw what 1 over x squared looks like. 1 over x squared, 1 over x, sorry. 1 over x, the graph looked kind of like this. It had a piece right here, and then it had a piece right here. I don't have it drawn at all right, correct, but it looked kind of like that. And you could graph it on your calculator real quick. But it had these two pieces. It had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So because we're shifting left 1 unit, it's going to shift the vertical asymptote over 1 unit. And we already see this right here. You can see more at the same time. Also, we can see that that's the vertical asymptote just by looking at this denominator. But because we're shifting up 2 units, the normal horizontal asymptote was at y equals 0. But now, because we're shifting up 2 units, the horizontal asymptote is going to be at y equal 2. Then what you can do is you can just maybe make a little XY chart and get a few other points. It's going to go through like, let's see, if x is equal to 0, let's just make a little XY chart here just to get a few more points. If we're equal to 0, I'm sorry. Then what would y be equal to? Well, y would be equal to -1 plus 2. So it would go through 0, 1. So the graph is going to go through 0, over and 1 up, like right there. And then maybe let's see, what else might we want to do? Something that would, well, let's see, we know it's going to go through there. And, oh, wait a second. Did I do that right? If x is equal to 0, yeah, that's right. And because that would be a minus 1 plus 2, which would be a 1. So let's see. What other point? What if x is equal to negative 2? Yeah, let's let x be equal to negative 2, because then we'll have a negative 2 plus 1. That's going to give me a negative 1. And so we're going to be adding 1 to 2. So that's going to give me negative 2, 3. So let's put that point in here too. 1, 2, negative 2, 1, 2, 3. I believe that's right. Because this is x equal negative 1. Okay, so we've got a couple points here. And then we know that it's going to be getting closer and closer to this horizontal asymptote, and it's going to be getting closer and closer to this vertical asymptote, going down, 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 down. Now I probably don't have this drawn just right. And it's doing the same thing up here. And I'm not sure I got that right. Oh, you know, I think I put that in the wrong place because I was counting from here. But it should actually be negative 1 over 1, 2, 3 up right there. And then it's getting closer to x equals negative 1, and it's getting closer to y equal 2 up here. And so y equal 2 is the horizontal asymptote. X equal negative 1 is the vertical asymptote. Now, the domain for this function, we can look at this function. What are the values of x? What can x be? Well, x can be everything except for the vertical asymptote, which was at negative 1. So the domain is going to be from negative infinity to negative 1, union with negative 1 to infinity. My pen's kind of going out on me right here. And then the range is going to be, well, look how far down we go and how far up we go. And do we cover all the y values? We cover all the y values except for the horizontal asymptote. So it's going to be from negative infinity up to 2. Skip over the horizontal asymptote, unioned with from 2 to infinity. So what I said, I'll just summarize this down here. The shift, the horizontal shift, which is left to right, shift the vertical asymptote. Okay, because shifting left to right, sorry, it's going to shift this vertical line right here. And then also, vertical shifts meaning up or down, shift the horizontal asymptote. And I'm just going to abbreviate HA for horizontal asymptote. Okay, so there is that example. Look at that. And then let's look at this is the last example. So I was talking about y equal 1 over x squared. Here is just the graph of y equal 1 over x squared. One way it looks different anyways is that instead of it having one piece in the first quadrant and another piece down in the second quadrant, it's got both pieces are above the x-axis, one in this quadrant and one in this quadrant. Now it has a vertical asymptote at x equals 0. So the vertical asymptote, x equals 0. It has a horizontal asymptote, y equals 0, and the domain is from negative infinity to 0, union with 0 to infinity, and the range is just from 0 to infinity because the graph doesn't go below the x-axis. It also doesn't touch the x-axis. So that should be a rounded paren. And then this is just showing the table from the calculator or some calculator. As the x is getting smaller, the y is getting bigger. And as the x is getting bigger, the y is getting smaller. So as x goes to 0, the y goes to infinity. That's the vertical asymptote, x equals 0. As x goes to infinity, y goes to 0. And that's the horizontal asymptote, y equals 0. So that's just what that's saying right there. So we're going to look at a transformation of that function next. And this will be our last example. Okay, so here is the function. Get it right. And notice, I know that it's a transformation of y equal 1 over x squared because the square outside the grouping symbol. So I'm going to rewrite it like this. Just it might help you see what the transformations are a little bit better. Plus 1. Okay, so it shifts the graph of y equal 1 over x squared. And this is how it shifts it. It shifts it, remember, this is going to shift right 3 units. And then it stretches by a factor of 2. So that just means the y values will be 2 times what they would be in y equal 1 over x squared. And then it shifts up 1 unit. Okay, so we know what the normal graph of y equal 1 over x squared looks like. It's got both pieces above the x-axis. That's y equal 1 over x squared. It's got, it's x equals 0 is the vertical asymptote, and y equals 0 is the horizontal asymptote. So what's going to happen, the vertical asymptote is going to get shifted right 3 units. So if we go over to 3, x equals 3, that's going to be the vertical asymptote. And then it says it shifts up 1 unit. So then right here at y equal 1, that's going to be the horizontal asymptote. So I think the best thing to do is to go ahead and draw in your vertical and your horizontal asymptote after the transformation. And then maybe you just want to get some other points. So maybe make a little XY chart. And we know x can't be 3. But what if x were 1? So then we'd have 1 minus 3, which would be a minus 2, but we'd square that, and that would be 4. So we'd have, I think, wouldn't it be like 1.5? That if x is equal to 1, yeah. So if x is equal to 1, the y is about 1.5. So we could find a few points just to sketch in like this. How about if we've got a 2? Then I'm going to have 2 minus 3 is going to be 1. And 1 squared, or minus 1, but minus 1 squared is going to be 1. So this is going to be 2 plus 1 equal 3. So you could plot as many points as you want here. But it's going to have the point 2 over. So 2 over and 3 up. Like that. And then you could plot some points over on this side as well, like maybe you go 5. So 5 minus 3 would be 5 minus 3 would be 2. 2 squared would be 4. So this is going to be 1/2 plus 1. It's going to be 1.5 again. So over here at 5, the y value is going to be 1.5, and on like that. So then I can just kind of sketch it in. It's going to look kind of like this. And you can also graph it with your calculator. And then it's going to be doing this over here as well. Kind of like that. Something like that. Okay, the domain of this function. Well, we've got to skip over the vertical asymptote. So the domain is going to be, it's going to be from negative infinity up to 3, union with 3 to infinity. And then the range, so we had the graph shifted up 1 unit. So the range is going to go from 1 to infinity and not including 1 because that's a horizontal asymptote that actually never touches that. Okay, so that's the end of this section. Page. Back on here. Okay. So I think that's all there is for this section. I'll assign your homework for this, and we'll cover the next section very soon. So I hope y'all are going to have a great spring break next week, and I will talk to you soon. Don't hesitate to call me if you, or not call me, but email me if you need me. Bye-bye.